Good morning. Today we're going to do part 5 of our Robots and Marbles tutorial series. Today we're going to be doing our first example with Network X, embedding essentially a graph database in each individual step of a cadCAD state. So to just recap, so far we've started with this basic example of you have a robot that has multiple arms that is moving marbles in between different boxes to try and reach an equilibrium. We've added Monte Carlo steps, we've added stochastic processes, we've added behaviors, and we've started to add more of these complexities. Today, we're going to be embedding that network object to allow essentially a scalable graph database that will allow you to have a bunch of different functionalities, which is a lot harder than hard coding if you say for behavior, agent behavior. Instead of having to have a separate mechanism and behavior and state for each different individual actor, now you can embed them into a graph database that only has, or network X object, a graph object that only needs to be updated through one mechanism, which is a lot easier to use. So essentially how we've changed this process is now we have n number of boxes, which we're going to have 5 in this example, and we have an m number of robotic arms, and what they do is that updates the balls, which updates the number of boxes. So we have this scalable process here that we'll walk through below. And this, as all the other tutorials, is posted online on our GitHub. And this is in the videos folder. Our complete write-up is in the Robots and Marbles Part 5 folder. So what we're doing here, and I'll live code this with you, is what we're doing is we have robotic arms. We have a number of robotic arms capable of moving the boxes around, and we're just importing the number of just standard functions plus the network X, which is new compared to our other tutorials. And what we're doing, we're defining our global variables here. We're going to have 5 iterations of our model, 5 time steps. One Monte Carlo run. If there's only one run, there's not multiple runs we're averaging for this example, but we're doing 25 state updates. In time, 25 time updates. And then we have 5 boxes in our network. And what we're first doing is just instantiating. We're going to have one run. We're going to have 25 times. This is the simulation parameters or sim parameters. This is a thing you should know pretty well by now, by heart. And then this is the new part. We're instantiating a graph object here. And this we're saying how we're defining the edges and nodes. We're basically defining this graph object we're using instead of some of the other objects is it will automatically connect all of the nodes with edges, which edges are lines and nodes are the circle parts of the vertices for the network. It depends on your terminology. And what we're doing here, we're just iterating through the nodes in the network, which we're defining as 5 different nodes for the boxes. And we are adding balls, a number of balls per those boxes. And we're doing a random integer stochastic process between 1 and 10 balls for each of those 5 boxes. We're just iterating through the network, and we've established the network here. And then this is at just the top of the state. These are global variables. This will only run once, and now for each of those 25 steps. And now what we have is we have the behaviors section, which we're defining. We're going to do deltas for the different network edges. So essentially what we're doing is taking the source and destination of each edge, and we're going to be checking to see if one node have more balls than the other node that's connecting, and then we'll have a delta to show the change. That's what we're doing here, and we're creating a dictionary of balls that we're going to pass through from the behavior step to the mechanism step. So what we're doing here is we're going to update the network based on those. We're taking a copy of the local network. The commented out here, we'll have a tutorial later about deep copying and for objects and things. So you're making sure if you have partial state updates, you're using the correct instance. So we can talk about that in a future video. And here we have delta balls. We're importing these balls from the behavior step into the mechanism step. And then we're moving the balls around based on the behavior, the robotic network, because we have a network of arms here is what we defined up in this aspect. And then as our state, which is where it's different, instead of defining 5 different boxes as states, we're defining network as a state, which includes all of this information. So we don't have one state variable for all of this information we're holding, which is where this gets really powerful when you're doing a lot of agent-based modeling and things of that nature. So our actions robotic network, our variable is the network or our state variable, and then we're updating network. So it's very simple wiring up of the system to be able to do this complex process. So then, so standard, we're just configuring what happened here, this partial state updates, initial conditions, simulation parameters, and then we're running it down here. But first, I'm just plotting what that graph looks like. So I will run that, then I'll run this, and this is showing our graph. Where our initial randomization, we have the 5 boxes as we spoke about. We have 1 ball in one box, 8 in another, 5 in another, 8 in another, and 6 in another. So we'll see how that evolves over time. So now we run cadCAD here. And then we've also defined, to be able to get, one of the tricky parts is once we're embedding now a network object graph inside of a pandas data frame at each time step, each of those 25 time steps, we need some helper functions essentially that we're going to apply, and I'll show you, to be able to get the values out of that network, and so we can plot it with Matplotlib, because we can't use some of the standard network X graphing functions because of how it's embedded now in a pandas data frame. So we have to bring it back out. And then here's something that just helps pad the files and stuff and make two-dimensional for plotting purposes. So we'll run those. And then essentially what we're doing here is we're creating a new variable in this data frame that's called balls. And balls is showing, now first I'll just show you what the data frame looks like. It looks kind of funky, like the network just says 0. This is defining how many boxes there are. And you can't really see any changes throughout time because it's an embedded object. That doesn't mean changes aren't occurring, it just means you can't really see it here. But you'll see that changes did happen. That's why I didn't really have that shown initially. We're creating a new column that's called balls, and what we're doing is pulling out the balls with using this helper function, using a lambda to apply it out of the network. So now if we look at the pandas data frame here, you see there's a list inside each of the network, each of the time steps that has a number of balls. And if you look, 8, 1, 8, 5, 6 is the same that we had up here. And you can see how this evolves over time. And now we'll actually plot this. As you can see, we get to, once we have an uneven number of balls and boxes, we're never going to quite hit the equilibrium. But as you can see, looking to be around time step 4, we start hitting, we're rotating between 2 separate equilibriums. Actually, no, it starts in time step 5 is where we start, which is actually 6 because we're using 0 indexing, is when we start rotating between the 2 different local optimas, not the global, because there's no global here in this instance. And when you plot this here, you can see this zigzag back and forth and what we did to apply this, we use this this make 2D and the pad function to essentially make this so we can plot it, and you can see it going back and forth. Now, if we run this one more time, you'll see a completely different result as we have the stochastic process in there building on the previous. And then we're working on adding, so you can, and it's a lot different here. Let me do it one more time. Adding Monte Carlo aggregation and things like that. There's lots of, we're creating more of these helper functions to do those sorts of things. And you can see the changes are different each time with the stochastic nature. Well, hopefully this has been helpful, and feel free to modify the code and let us know any other questions you may have or any suggestions you have to improve it. And we will continue making cadCAD the best simulation tool in the scientific Python ecosystem. Hope you enjoyed.